Okay, so the presentation has 5 parts. In the first part, an introduction, then the structure analyzing the determining of the stress values for the existing and the proposed structure, the assessment of the defects using the engineering critical assessment, and the fatigue assessment in the 4th part, in the conclusion in the end. That's about the introduction. So the rehabilitation of this historical steel structure is a sustainable development goal of European Union. Of course, in Transylvania, Romania, there are a relatively small number of steel bridges older than 100 years old. Sorry, I do not know why they are. Maybe it's better like this. Sorry for seeing also but I do not know why they are. The presentation is. You can see right now. Okay. It can be seen or not. Sorry.
Yes.
Sorry. Okay. So in Transylvania, as I said, there are a major part of these bridges due to the Austro-Hungarian being an Austro-Hungarian part. They are considered, these bridges, also witnesses of the past, and the importance is that we need to have them consolidation and maybe retrofitting. As a case study, I will present a riveted road steel bridge built in around year 1925. I will present a solution for consolidation and retrofitting for this bridge, taking into account also the structural integrity assessment. For the phases of, let's say, the research, it was done first the structural analysis of the existing steel bridge, and then, of course, the structural analysis of the proposed solution, the retrofitted bridge, together with the engineering critical assessment, considering the most possible discovered flaws. This was needed to do because of the age of the structure, the steel bridge, and it was needed to reveal the indication of the possible discovered flaws and, of course, the future one. In the end, of course, the fatigue assessment, as I said before. Regarding the geometry of this bridge, it's a 27.86 opening bridge. It's 3.6 for the deck. From the other side, we will see immediately in the other slide. Regarding the members of the elements are made of composed profiles, usually from angle profiles, 100 to 120 millimeters, together with steel plate-like stiffeners. As I said, it's a 6.35 opening on the X direction. On the Y, it's 27.88. We can see here that we have parabolic shape truss beam side beams, and of course for the deck, longitudinal transversal beams. The pavement is sustained by some so-called Zores profiles. We will see in some images. There are some omega profiles that are sustaining the pavers because the deck is made with the pavers. And of course, as I said, the deck is consisting of a network of beams, transversal and longitudinal. Some details regarding the existing structure, 600 millimeters transversal beam, composed type 1, and longitudinal beam of 320 millimeters high. An image of the steel bridge. As we can see, there is a corrosion, but not so much. So it will be very easily. It can be done by sandblasting and, of course, by painting. The Zores profiles, you can be see here, of course, the implication of the ballast and the pavement because of the water drainage and affecting the steel structure. All the all the joints are, as I said, riveted. There is no welding because in that time it was this was the solution for the bridges in our area, of course. Regarding the second part, the structural analysis, it was done to analyze the one, as I said, for the existing structure to see the stresses, and of course then comparing with the proposed solution. So for the existing structure, it was determined stresses in the main elements: girder, chord, lower chord, upper chord, the diagonals, and the deck profiles. Here there are presented some slides regarding the final element analysis. And for the proposed solution also, as we can see here, is presented also this solution. So we do have the existing structure that will be cut in half, and in the area, in the middle area, it will be erected a beam that will be a carrier beam, a longitudinal one. In this way, it will not be needed middle, let's say, middle sustain point. So this will be having a good implication of the structural behavior, because it will take almost half of the loading. We will see also in the stresses values. So it is a box girder for 600 millimeters per 1.1 meter, 1,100 millimeters height. And of course, it will be needed also some elements, transversal elements that will be connected with the existing structure through bolts, so through a bolted joint. Here it can be seen also better with from the analysis software. So we do have the structure with the red color, the main beam and the transversal new elements. It will be HEA 600 and the existing structure with different colors. Of course, it will be needed also new bracings for the deck. The values of the stresses are represented in this slide. So we do have the main elements, lower and upper chord of the truss beam, diagonals also, deck, transversal and longitudinal, transversal and longitudinal, yes, because it's secondary beam. And for the proposed solution, the deck main beam that is having the higher stress, of course, due to the higher loading of it. We will retain each this stress because we will use in the further assessment of the implication of the flows. The third part of the presentation is of this research is regarding the engineering critical assessment that it was needed to be done, as I said, considering the existing structure. So in our research, of course, it's regarding during the operation service in order to assess the flows found in service and to make the decision is needed to repair or to if it's safely to remain like this. This slide is presenting the different kind of approaches in the mechanical engineering and the civil engineering structure applications. Considering the presence of the defect, as we know in the mechanical engineer application, the defect is presented before the design and manufacturing, considering as a data, input data. In the civil engineer structure, unfortunately, we cannot consider these defects due to the imposed norm. Of course, we need to have the details be respected as set the norms, as for example, the design of steel structure, material toughness, and design of steel structure, the fatigue, Eurocode type norms. And the defect is present in the last part, in the inspection area. So when we do have the inspection done, we discover the defect, and of course, in that time we do need to have a solution. So the research is proposing to have, let's say, to know the implication of the possible discover flaw and to know if these flaws, considering the new retrofitting structure for this new retrofitted bridge, will have big implication, considering that it will be needed to consolidating or not. So it was used the engineering critical assessment methodology that is proposing two phases. First is determine the critical, the acceptability, the critical size of the defects, and the second phase, of course, the fatigue assessment based on the loading events history. So I'll present very fast. I'll try to fit in the timetable. So to present these two phases. So first, it were taken into account the British standard 77910 norm that is proposing these types of flaws and, regarding the dimension and their interaction. So these types of flaw, the through thickness flaw, embedded, and the surface flaw, you'll see you have also long surface flaw taken into account. And it was used the failure assessment diagrams, level 2 in this case, in order to assess these implications of the possible discovered flaws. Sorry, just a moment. Okay, so this is the crack assessment, admissibility assessment for fracture resistance. So this is the let's say the idea in the background of the failure assessment diagrams, considering the LR and KR ratios, the LR, the tension, the stresses ratio, and the stress intensity factor, and the fracture toughness of the material, considering for this failure assessment level 2, considering these phases of the calculation. First is determining the stresses that we already have done. Have calculated PM membrane respectively bending, primary and secondary, and then we need to determine the ratio of the stresses LR and the KR, the ratio of respectively the stress intensity factor and the fracture toughness. In the end, we will have coordinates that will lead to the assessment point, having the assessment done. So for this, for the in case steel bridge, we did use the values of the material tensile stress testing for the yield and the ultimate strength, and we did use a SYNTAP procedure to evaluate the fracture toughness of the material, having the Sharpie test done for some specimen taken from the bridge structure. It were considered, as I said, five types of flaws: true thickness, surface, long surface, buried, and edged flaw. Each case of a flaw is taking into account the type of the flaw and the position of it. So we do have true thickness flaw in the main truss beam, lower short, and of course we'll have also the dead longitudinal or transversal beam. So these flaws together with the location combined are 25 cases in the end. For these 25 cases in the end, we will have also the values of the point, the position of the assessment point for the level 2 assessment diagram. In the end, having these graphs and some conclusion and results, discussion and upon the results. So we'll have some issues with the TEC longitudinal beam. As we can see here, it is a sensitive flaw for 30. It was taking the 30 millimeters flaw. It was over limit the flow length, critical length of 28 millimeters. So each type of group of flows were assessed, and for each type it was done this assessment. Of course, in the end, proposing also the determination of the critical size of the defect. So here are some, let's say, presentation of some results for this assessment. As we can see, for the main beam lower chord, the long surface flow is also over limiting the critical flow length. Also for the main truss beam, the buried flow, and respectively the diagonal main truss beam, the flat plate edge flow. It were calculated also the flow height, critical length, and flow height and flow length critical values in the end for the future assessment. Coming to this future assessment, fatigue assessment. So we done the stress ranges as needed to have as a data for the input for the fatigue assessment. We do have we do need also the limit of the crack growth, following the failure assessment diagrams, and the fatigue crack law is with Paris law with one slope of 2 stages. And the types and the dimension of the flow. These are the input data. We did establish the loading, considering a load spectrum for a given in time. It was done, the distribution of the loads was rearranged following the probability density function using a Weibull distribution. And in the end, using a rainflow algorithm, the results were processed and determined a block of stresses with stress ranges and the previous frequency. Block of stresses, each block representing 1 year per stress. So we can see here for the main beam, because the research was done only for the main beam of the deck, not for the other elements, because it's very difficult to, it's a lot of data to be processed. So we do have the research done only in this point, only for the main beam. So here are the results for the block of stress ranges and the frequency of these stress ranges. As I said, for the main beam only, it was done an assessment for 5 types of flow, as I presented before. And in the end, we come to this graph. This is a very important graph, in which we determine the number of blocks, number of years, considering the flow dimension, the number of years needed to have a crack starting from a point to be extended to the critical size of crack. And in this way, we determine the implication and the service life for the service life time of the structural element. As we can see here, for the main beam, edged flow is having a 10.6 year. In 10.6 year, it will reach for a flow for 2.25 millimeters, which is the critical size of the flow. And of course, another problem, it will be for the long surface flow that will reach in almost 2 years, 1.92 years at the critical value of 5.36 millimeters. The graph is presented in a logarithmic scale due to the ease of the representation. As a conclusion, and maybe some discussions, it's better to, of course, it's better to retrofit and consolidate, considering that we do have a historical bridge, but in this case, it was also more economically speaking, as we do have around 33 tons per existing steel bridge, and in the solution of retrofitting, considering that we do have 2 ways of for traffic, we will have 63, almost 63 tons per the bridge. So in the end, it is from our thinking, it's a good economical situation, let's say, for this solution. So the solution is considering also, as I presented, the engineering critical assessment in order that to assess this implication of the possible discovered flows. And also this was presented in this research. I said also this, and in the end, as we have seen, our presented graphs, comparative graphs for the structural and service lifetime, taking into account different types of flow and locations. So thank you for your attention. Sorry for being having technical problems and maybe being so long for my presentation. So thank you again. If there are questions, I'll be happy to answer.